Hello, welcome to Calculus 1, Lesson 1C.3, and Behavior Part 2. Let's talk about what it would mean for a limit that goes off to infinity to actually exist. Right, because if a function is going to infinity, going up, increasing without bound as x gets large, we would say that does not exist. But when we picture something like 1 over x going down and trying to meet the y-axis, we feel like that limit should exist. We feel like it's trying to settle at 0, even if it never quite touches it. Okay, your horizontal asymptote. That's what it wants to look like for a limit to exist. Here's another example of what it looks like for it not to exist. So what I mean by settle is it's not going to average out in any way. Cosine of x makes a wave. And it does that forever and ever and ever and ever and ever and ever. Okay? As x goes to infinity, cosine of x oscillates between 1 and negative 1. Between negative 1 and 1. So does it average out in the middle? Can we say, because the average of negative 1 and 1 is 0, can we say the limit as x goes to infinity of cosine of x equals 0? Because it spends its time equally above and below that? Actually, no. Because it doesn't settle. Okay? For this limit to exist, it would have to try to get close to 0. Even if it never quite touches it, it has to try to get close and then stay close forever. If it then leaves periodically, that limit would not exist. Now let's talk about this with epsilons. This is probably your first exposure to the idea of an epsilon. So here's the definition. The statement, limit as x goes to infinity equals 0, would really mean that for any epsilon greater than 0, we can always find some big number m, so that whenever x is bigger than that m, we are guaranteed that our function stays within epsilon of 0. Okay, so let's break that down a little bit. So for any epsilon greater than 0, this is a tolerance. And we think of an epsilon as a very small number. This m greater than 0 means that once x is big enough, once x is beyond this m, we forever have it where the function stays within that tolerance. So the function value, the y value, is within that tolerance of 0 and stays forever. Okay, so once x gets beyond m, the y value is never going to go above epsilon or below negative epsilon. Is another way to read that. This is easier to see if you use an actual example. Let's use the epsilon definition to actually prove that the limit as x goes to infinity of 1 over x squared is equal to 0. Okay, so we're going to start with an arbitrary epsilon. So an arbitrary epsilon, this could be any small number. Technically, I suppose it could be a really big number or two. It could be 10,000. But we don't think of it that way because letting your epsilon be big like that, it makes everything trivial. So you want to picture that epsilon is going to be 0.1 or 0.01 or 0.0001, something very small. We want to find some number m so that when x is beyond the m, the y value, which is 1 over x squared, has to be less than epsilon. And there should technically be absolute values around this, but 1 over x squared is always positive anyways. So we're fortunate here that we get to let those absolute value bars fall off. So here's the question. How big does m have to be to force 1 over m squared to be less than epsilon? Well, this is an inequality, and we can deal with this by isolating the m. So if I take the reciprocal of both sides, that's going to flip the direction of the inequality. So we need m squared to be greater than 1 over epsilon. If m squared is greater than 1 over epsilon, I can also take square root of both sides. Say m is greater than 1 over square root of epsilon. Okay, so this is the important bit here. If x is greater than, so m could be any number that is greater than this. So it could be this number plus 0.00001. So if x is any number that's a little bit bigger than that, then by transitivity, since x is bigger than this, and since x is bigger than the m, and the m is bigger than the 1 over epsilon, 1 over square root of epsilon. So x would have to be bigger than 1 over square root of epsilon. The question is, not highlighter, question is, does this guarantee that 1 over x squared would be less than epsilon? And if you look at this, if we manipulate this inequality now, we can get back to here. So take the reciprocal of both sides. And then square everything. So we have what we want. Let me show you what's going on in the graph. So here I've plotted 1 over x squared, and I'm going to start by letting epsilon be, let's go with 0.4. Okay, so I'm asking the question, I'm going to set my tolerance to be 0.4. Okay, I'm going to be satisfied that this function is going to 0 as long as I can show that it's going to get below 0.4 and stay there forever. Okay, so visually we can already see this function value is below this line, and it's going to stay there forever. Okay, so the distance here, this vertical distance between the x-axis and the line y equals epsilon, that's your tolerance. How far do we need to get to guarantee that that happens? That is your m. So here, m is 1 over the square root of 2/5, so 1 over square root of epsilon. This shows that once you are beyond this line here, you're going to stay underneath your epsilon line forever. And if I change epsilon to be something smaller, because of the way I, program this symbolically in GeoGebra, if I change epsilon to be something smaller, like 0.2, then the tolerance gets smaller, and this line, the m, has to move further to the right in order to guarantee that we're going to stay underneath that. Okay, so there's 0.2, here's 0.1, then we need to be at, 1 over square root of 1/10, and so on. So as I move epsilon out further, the spot we need to get to in order to guarantee that your function value stays underneath epsilon forever will move to the right. Your x will get bigger as your epsilon gets smaller. Now, because we have proven this, by this argument that we did over there, we didn't prove it for 0.05. We proved it for an arbitrary epsilon. We proved that no matter how small I make this, even if I make it 0.0001, I don't even know where that's going to end up. There it is. We proved over here that for an arbitrary epsilon, no matter how small we make it, we can always find an x such that going beyond that x will guarantee you're below the epsilon line. All right, I hope the visuals help. Ready for a harder one? Use the epsilon definition to actually prove that the limit as x goes to infinity of cosine of x over x is equal to 0. Now here we are going to use squeeze theorem. Squeeze theorem is going to help us a lot here. I'll show you what squeeze theorem is. It says if the following are true, if G is sandwiched in between F and H, and we know what a limiting behavior is for for F and H, and those things are equal, then that's got to be true for G as well. Okay, so I can make a visual over here. When C is infinity, C can be infinity for squeeze theorem. Okay, so you have some kind of function that is sandwiched between two others. Okay, if you know where these two are going and it's the same, and the other one is sandwiched in between, right? If both of these two functions are going to 0, and this wavy one is always in between the other two, then necessarily that one has to go to 0 as well. Using -1 and 1 for a trig function is really your classic example of an application of the squeeze theorem. We're going to say that since cosine always lives between -1 and 1, then this is true as well for positive x. Okay? So, if we want cosine of x over x to be less than epsilon, it is enough to show that 1 over x is less than epsilon. Because if 1 over x is less than epsilon, then necessarily cosine over x is. So the m that will work for 1 over x will also work for cosine of x over x. Which means from here, because of the squeeze theorem, we kind of get to ignore the cosine and just deal with the 1 over x, which is pretty easy. So once you understand the squeeze theorem, this question actually ends up easier than the previous one. So, how big does x need to be in order to ensure that 1 over x is less than epsilon. To find out, we're going to take the reciprocal of both sides. X has to be greater than 1 over epsilon. So 1 over epsilon is going to be a big number. X has to be greater than whatever that is. Okay, so what we find is if x is greater than 1 over epsilon, then cosine of x over x, which is less than 1 over x, is necessarily less than epsilon. Okay, so we're gonna let m equal 1 over epsilon. Cool. And this is for arbitrary epsilon. It means no matter how small I make epsilon, I can get this function to get underneath epsilon and stay there forever. Okay, let's look at the visuals. This one's actually kind of cool. So this area here, this dark purple area, that's the area in between. This is positive 1 over x and this is negative 1 over x. And cosine of x over x is always going to live within that shaded area, within that green area between the two curves, negative 1 over x and 1 over x. Okay, if I let my epsilon be, let's start with 0.4 so that it's easy to see. It's 2/5. Okay, and this is saying that x just has to be 1 over that. Okay, so this line represents where x is. Here's the epsilon line. Here is the tolerance that we want to be within forever after this line. Okay, so what we've calculated here is that as long as x is greater than, this would be 5 over 2, it is guaranteed that never will this function go above epsilon or further away from 0 than epsilon. It's going to stay between the positive and negative epsilon for its y value forever. Right? It's shrinking down to 0 because it's never gonna go back up or go back down any further than that. Okay. Now from here, if I change epsilon to be something smaller, such as 0.2, then of course the x has to move out further in order to guarantee that. Okay, so once x gets beyond this red line, we know that our function cosine of x over x will always be less than epsilon. I'll show it for 0.1. Okay, so it's always going to be between there, within that tolerance. So this is what it means to settle. It gets close to 0 and stays close forever. This concept of the epsilon allows us to quantify what it actually means to be close. So it's close if it's within your tolerance, which is epsilon. Okay, so when x is big enough, when x is greater than 1 over epsilon, we know that the y value will be close enough to 0 by this calculation. Cool, huh? Continuing from this previous, if epsilon is 0.002, find m and show that it works. So we said the m that we were interested in is that 1 over epsilon. So let's let x be anything that is greater than m, where epsilon is 0.002. What is 1 over 0.002? It's 500. So what we really want here is to let x be anything bigger than 500. Then we would have cosine of x over x, cosine of that big number divided by that big number, which is less than or equal to 1 over x. Okay, if x is greater than 500, then 1 over x has to be less than or equal to 1 over 500, and 1 over 500 is equal to 0.002. This shows that when epsilon is 0.002, going out to 500 or more, we'll keep cosine of x over x within 0.002 of 0. You want to see that on the graph? So there's 0.002. I'm going to need to go all the way out to 500 for us to be able to see this. It's going to be really, really squished in. So there's 500. And we're going to have to zoom in really, really far in order to be able to see what's going on, because 0.002 turns out very, very small. Okay, so this blue line here represents y equals epsilon. This is the line y equals 0.002. Okay, we're saying once we get beyond 500, this red line, the function is never going to rise above, or it's never going to rise outside of the area bound by the two lines here, because the green area is contained in there. And it looks like the green area is now, bound by straight lines. It's really not, right? Like it's shrinking down to the x-axis. It's just doing it very, very slowly. You can see cosine of x over x is oscillating in there as we get bigger and bigger and bigger. But it never goes outside of the green, which will always be contained between those two lines. If I go out far enough, you should see a gap between the green area and the lines that are framing it. If I can zoom in far enough, yeah. So the green is going to shrink down even closer than these. Right, so I could make epsilon a little smaller, and then we might need to address that gap there by moving x out further. So those are epsilons for limits going to 0. We can also talk about that for limits that don't go to 0. There was an and deltas there, but that was not correct. We're just going to pretend that's not there. So here it is when it's not 0. It's just some finite number L. For any epsilon greater than 0, we can always find some m greater than 0, so that when x is greater than m, it is guaranteed that the function value will be within epsilon of L. infinity. So for any epsilon greater than 0, this is your tolerance. We can always find m greater than 0, which makes when x gets big enough, the function value f of x is within epsilon of that number L. It might be above it, it might be below it, but it's no more than epsilon away. Cool? Now we can talk about horizontal asymptotes in calculus language. We're going to say that y equals L is a horizontal asymptote of f of x when either the infinite limit of f of x goes to L in the plus or minus direction. You could have one or the other, but not both. You'd still be able to say that there's a horizontal asymptote there. What about things we expect? We had things we expect for finite limits and for limits to infinity. What about for limits that go to infinity? End behavior. Assume that as x goes to infinity, your f of x goes to L. So we're assuming that f of x does have a horizontal asymptote, and so does g. They might not be the same, but both limits are going to exist and are finite. The limit of the sums will be the sum of the limit. So the limit of the sums limit as x goes to infinity of, it should be sum, limit as x goes to infinity of f of x plus g of x, and the sum of the limits is one limit plus the other limit. So this things we expect theorem says that those two things are equal, and that would also be equal to L plus K. It does work for products as well. The limit of the product is the product of the limit. Limit of the product is limit as x goes to infinity of f of x times g of x. So all of that is under that limit. Product of the limits is going to be, I'm going to make big parentheses, limit as x goes to infinity of f of x times, another big parentheses, limit as x goes to infinity of g of x. And this theorem states that these two things are equal, and that would be L times K. Okay, we have products, but we do not have quotients. Quotients may or may not obey the limits there. So the limit as x goes to infinity of f over g may or may not be L over K. It could be infinity, and it could be 0, and it could not exist. We also have that coefficients can come out of the limit operator. So if you wanted to talk about the limit as x goes to infinity of some a times f of x, that would be the same as a times the limit, which would be AL. Your quotients could do anything. It's hard to predict. For this, there's something called L'Hopital's rule. which you would learn later. Can't do that until you have derivatives. Speaking of derivatives, this ends Unit 1, so our next lesson we will be building up towards what is a derivative and how do we take it. So I'm excited to see you come back for our first lesson on derivatives at the start of our next unit. So as I bring this lesson to a close, I want you to know that I'll take the limit of your learning to its end behavior if you just give it a chance. That's my math pun of the day, I guess. It wasn't very good. At any rate, now you know something about end behavior. Keep practicing and have a wonderful day.